Most textbooks split rotational motion into two chapters. From your perspective, it's really all the same stuff. What's happening now is we are learning the entire course all over again and allowing for rotational motion. Up until now, every object we looked at was a point object because we didn't have the tools for dealing with rotation. When things have dimension, they can rotate, and we have to be able to deal with that. So we viewed every object as a point object. All the mass was located in a single point. We didn't have to deal with rotations. All we cared about was translational motion, things moving in straight lines. And we covered all of our topics in the first 9 chapters or so. And in the next couple of chapters, we're going to do it all over again, but including rotational motion. Let's take a look sort of topic by topic. The first thing we did was describe motion, translational motion, things moving, things translating from one place to another. And of course, in order to do that, we have to define position, velocity, and acceleration. So when things move in one dimension, we have x for position, v for velocity, a for acceleration. And when the acceleration is constant, we can come up with these kinematics equations. Things like v final is equal to v initial plus at, or x final is equal to x initial plus v initial t plus 1/2 at squared. And there are a couple of others. Now we're dealing with things rotating. So instead of position, it makes sense that we have some kind of an angular version, an angular position. We use theta. It makes sense now if we have some kind of an angular velocity. We use omega. What does omega tell us? Omega tells us how theta is changing in time, just like v tells us how x is changing in time. And we want to know how omega changes in time, just like we wanted to know how v changed in time. We came up with an acceleration a. Now we have an angular acceleration alpha. And when alpha is constant, we can come up with kinematics equations for rotational motion. And because we're going to derive them the exact same way we did for translational motion, they're going to have the exact same form. Only every place you see an x, there'll be a theta. Every place you see a v, there'll be an omega, and the a's become alphas. So we'll have something that looks like omega final is equal to omega initial plus alpha t. Theta final is theta initial plus omega initial t plus 1/2 alpha t squared. And the other ones follow along similarly. So this is the first chapter using theta, omega, and alpha instead of x, v, and a to describe motion and come up with rotational kinematics equations. The next topics were Newton's laws. The first thing we had to define was something called inertia. Newton's first law: every object that has mass has inertia. That's how we measure inertia. We measure inertia with mass. And that a force acting on the mass changed its motion. So we had force, and Newton's second law put them together. The sum of the forces is ma, mass times acceleration. And how did we solve these problems? One of the tools we used was free body diagrams. We started out by drawing a free body diagram, but our view of the world was fairly simple, and every object was a point object. So how did we draw a free body diagram? We started with a dot that represented our object, because that's what it looked like to us, a little dot of mass. And then we would put arrows on there for things, a normal force, a friction force, things like that. So our free body diagrams look something like this. Now we're going to look at this from a rotational motion standpoint. What is our inertia now? Instead of just mass, it's a little more complicated. It's not just the mass, it's where the mass is located with respect to the axis of rotation. We use I for rotational inertia, and that's going to equal the mass times the square of the distance between the mass and the axis of rotation, mr squared, for a point mass. Instead of using force to figure out how the motion changes, we use something called torque, and we use the Greek letter tau. And Newton's second law now becomes, what do you think it's going to become? We're going to replace force with torque. We're going to replace mass with the rotational counterpart for mass, rotational inertia, instead of our inertia that we've been using. That's I. And we're going to replace A with our rotational acceleration, alpha. Sum of the torque equals I alpha. Our free body diagrams are going to change a little bit also, because we don't just care about the fact that forces are being applied to our object. We care about where they're being applied to our object, because if they're applied in different places, they may or may not cause our object to rotate. We'll draw what's called an extended free body diagram. So I'll do one for pulley. Pulley is going to have weight and maybe a tension. Maybe there's a rope pulling on it over here, and maybe that rope continues around and is also pulling over here. Then there's probably some kind of a support force. So this is a free body diagram more like what we would draw now, an extended free body diagram. You draw the shape of the object and you actually include the location of where the force is being applied, because that's important for rotational motion. One quick point here. When we've used pulleys in the past, we've always said that they were massless because we didn't know how to deal with rotation yet. We had to keep our problems simple. Now we're learning how to deal with rotation, so our pulleys can have mass. And when the pulley was massless in the old days, right, a couple of weeks ago, the string had the same tension on both sides of the pulley. Now that we're including the mass of the pulley, the tension will be different in the string on either side of the pulley. The next topics we hit were energy, including conservation of energy. One of the types of energy we talked about was kinetic energy, energy of motion. And when things are moving, translating, moving from one place to another, our kinetic energy, 1/2 times the inertia times the velocity squared. What do you think the rotational form will be? Because something might not be translating, it might not be moving from one place to another, like our pulley above. It's fixed to the earth by its axle. It's being held to the earth right there. What happens if that pulley starts spinning? Don't you think it's going to have some kinetic energy? Every little chunk of mass in the pulley is going to be moving. It's going to have some kinetic energy. We call that rotational kinetic energy. I'll put a little R subscript on my K there to indicate its rotational kinetic energy. So what do you think the form is going to be for the rotational kinetic energy? We're going to substitute for the inertia, the rotational inertia I, and for the velocity, the rotational velocity omega. So rotational kinetic energy, 1/2 I omega squared. And the same way we did energy conservation problems with the initial mechanical energy plus work done by external forces plus work done by non-conservative forces had to equal E final, the mechanical energy at the end of the problem. We'll use the same setup for our rotational energy, but we're adding one more term, K plus U sub G plus U springs, initial and we get the exact same thing now for rotational, only we include one extra term. I'm going to put it right here. K plus K rotational plus U sub G plus U springs at the beginning. Same thing at the end. Okay, you get the idea. We're adding one more term because our view of the world is getting a little more complex. This equation for energy, we're going to use that for a long time in our career in physics. But as our view of the world becomes more complex, so we can deal with more real-world situations, because in the real world things have dimension. They can rotate. Now we have the ability, we've added a term to account for that. Next term, you'll learn that not every object is electrically neutral. Right now, we don't think about electric charge. Everything is neutral. You'll learn soon that objects can have electric charge. And electrically charged objects exert forces on each other and have energy between them. And so we'll add another term in here for the energy stored in an electrical interaction between two objects. And our energy equation will get a little bit bigger and account for a little more complex view of the world. Or maybe I should say a more realistic view of the world. And the last topic we covered was momentum. What was momentum? We used lowercase p, the inertia times the velocity. Now we're going to have a rotational counterpart for momentum. We call that angular momentum. We use a capital L. And what do you think the angular momentum might be equal to? Let's replace the inertia with a rotational inertia. Let's replace the velocity with a angular velocity. With angular velocity, and we get L equals I omega. Conservation of momentum told us that the initial and final momentum were equal if there were no external forces acting on our system. And we could use that to solve problems, particularly those involving collisions. And the same is true for our angular momentum. We're going to use conservation of angular momentum to solve problems involving things that are rotating, things that collide and cause rotation, situations like that. Everything we've done so far this quarter, we're going to redo it in the next couple of chapters using rotational counterparts for all the things we've learned so far. That's why I say over and over again, physics builds on itself. Hopefully you've got a good foundation so we can keep building.